Yes, well, I don't know about entertaining, but what I would like to talk about is geometry of the FBI transform. So this is a point of view that is largely due to Chestrand. Let me remind you about this FBI transform. So we had a transform TH, which took, well, it takes many spaces to other spaces, but let's talk about L2 of Rn. It takes it to this L2 phi, which is L2 on Cn, but with respect to a measure 2 phi over h and then Lebesgue measure on Cn. And it's defined as follows: THU of Z is equal to, well, there's some constant Cn h to the minus n 3n over 2, 4, I don't remember now, but let's not worry about this, E, and I'm going to write it now like this now, phi of Zx, u of x dx, where phi Zx was 1/2 I x minus z, or z minus x squared, and the capital phi of z was defined as the imaginary part of z squared. But if you look at this function here, you know, we wrote it last time, so this is 1/2 I z, real part of z minus x squared, plus, geez, I'm sorry, somehow this chalk, real part of z minus x, imaginary part of z, plus minus 1/2 I, imaginary part of z squared. So this phi of z actually is the maximum of minus imaginary part of phi. So this is the maximum over x in Rn of minus imaginary part of phi zx. So of course, you know, this is just a transformation. So what's the geometry here? Well, for the geometry, let me remind you of some linear algebra. So I have a vector space V over a field F of characteristic 0. And the two fields we'll consider today are complex numbers and real numbers. Okay. Hey. And then from this vector space, I form another vector space, V star, V star, okay? And that vector space is equipped with a symplectic form. Symplectic form, which is a quadratic form between two elements, which I write as x psi, say, and y eta, and that is the same as psi applied to y, if you like, minus, but I will always just write it like that. So when in the context of linear algebra, I just use brackets like this, psi y minus eta x. Yes, so if you like, it's an action of the V star on this. And of course, so this is a symplectic form. But that's not the only symplectic form you can have on this. Symplectic form, even just a constant coefficient form, is just a quadratic, non-degenerate quadratic form, which is antisymmetric. So for instance, if I consider V to be Cn, I can think of it as a complex vector space, but I can also think of it as a real vector space. Yes? And then on this, we have various symplectic forms. We have this symplectic form, which is a complex symplectic form, which is complex linear, but we can also take the real part of this, which is now a symplectic form with the field being R, or we can take sigma imaginary, which is the imaginary part of the symplectic form, if I think about it as a real vector space. So what is the geometry here? Well, let me first, I'm not going to really elaborate on this, but let me point out that there are some essential properties of this phi that we use Namely, in this setting, we could just replace phi by an arbitrary holomorphic quadratic form. On Cn cross Cn. And what we have is the property that the imaginary part of this, when I take a second derivative with respect to x, is a non-degenerate. So imaginary part of the Hessian with respect to y is positive definite. Well, certainly it's true. I don't know how I write it, 0, I suppose. That certainly is true. If I differentiate twice with respect to x, I get 1/2, identity times I. So imaginary part is positive. And the next property we want is that the Hessian, or the mixed Hessian x, sorry, not yy, xz is different from 0, okay? We have this non-degeneracy property. All of these conditions satisfied in this case, and you can just, think about this. The generalization involves some linear algebra, but it's fairly straightforward. And this is what we would call a linear theory, in a sense that the phases that we consider quadratic. So if you survive till my last talk on Friday, I'll mention the importance of nonlinear phases in this business and the flexibility that they afford. And this phi then is defined by this formula. And under these assumptions, one checks using linear algebra method that this has the property that the Hessian with respect to z and z bar, so this is now a real function of z, is positive definite. In fancy parlance, this means that phi is a strictly plurisubharmonic quadratic form. Huh? So what is the geometry here? Well, as actually we will hear tomorrow from Alex in a different setting, if one forgets about the fact that this phi is complex, though of course it has a real part here, this is an operator given by an oscillatory integral with some, of course, complex part, but this complex part is actually very nice here. That's this condition here. It's a Gaussian. So in the case of any, an oscillatory operator given by oscillatory integral, we associate to it a canonical transformation. And that canonical transformation is given implicitly by this expression here. And the implicit function theorem, which of course in linear algebra is an exact thing, tells us that this actually defines a linear transformation because of this condition here. Okay? So it's all just linear algebra. Of course, I can't resist telling you, I never actually took a course from him, but one of my professors at MIT when I was a student, still there, Mike Artin, one of his students told, a famous algebraist, one of the students told me that Artin said that we only do the rest of mathematics because linear algebra is too hard. And several years ago, I sort of saw him in the corridor there, and I said, Professor Artin, one of your students told me that you said this. Is that true? And he says, I don't recall saying this, but it does sound like something I would say. So he didn't quite deny it. But indeed, this is easy linear algebra. So this shows that this is a linear map, and this is symplectic. You check it by, the easiest way to check it is by thinking about this form here in differential terms. So in these coordinates, it's a form, for instance, it's a form d psi wedge dx, where I think about it like, it's a sum of d psi j wedge dxj. And then if you just take, dx wedge d of this, and you check easily that dz is equal to that this is equal to dz wedge d of this by Clairaut's formula. So this is a complex symplectomorphism. So this is over this field F. Complex symplectomorphism. Symplectomorphism means that we preserve the symplectic form. And you see, in this FBI business, what we are doing is we are taking functions of Rn and taking them to functions of Cn. The phase space, sort of quantum mechanically corresponding to L2 of Rn, is the cotangent bundle of Rn. So Rn is now my V, and it's Rn cross Rn with the standard symplectic form. So we are interested in K phi of Rn cross Rn, or if you like, T star Rn in fancy parlance. And what is it? Well, let's do it in the case of an example. What is K phi in our example here of this function? So I will differentiate it with respect to x, and what I get here is z minus x times I, and this gets mapped to z I, also z minus x. Did I do my linear algebra right? Hey, guys. Now this is, no, linear algebra is too hard. So if I now want to solve, I want to solve for these two guys in terms of x and xi. X and xi goes to x minus I xi. And you already see something interesting from this geometric point of view. You see, when we define the wavefront set, if I had used some distribution, we said that x naught, xi naught is not in the wavefront set of U if and only if there exists U, a neighborhood of x naught minus I xi naught inside of Cn and some delta which is positive, such that th U of z is less than this e to the phi of z over h minus delta over h. We gain something over just the basic bound. But where is, it's a neighborhood of what point? It's a neighborhood of x naught minus I xi naught, I xi. And this is the precisely why, because x xi corresponds to x minus xi in the complex. And what is the image here? Well, the image I calculate, that is simply x minus I xi for x real and xi in real. And this I can write as z, and what is xi? Xi is the minus imaginary part of z. Yes? Z in Cn. And that's a graph of z, 2 over I, a holomorphic derivative or differential of phi, z is in Cn. And you can check linear algebra that that's true for any quadratic form with these properties, where phi is this function here. Okay? So this is now, so we call this lambda sub phi. And that is now the phase space on the FBI transform side. And, you know, it's now a graph over those complex numbers. And, you know, maybe just for, you know, aficionados of symplectic linear algebra or geometry, this is an image of a real symplectic manifold. Yes, the real symplectic form on the Rn cross Rn agrees with the real part of the complex one. So this means that this guy here is actually a symplectic manifold. Because, well, this does not follow immediately, but it actually is a symplectic manifold with respect to the real symplectic form. And because the Rn cross Rn has the property that the imaginary part vanishes on it, the image will also have it vanishing on it. And it's a Lagrangian with respect to the imaginary part of the symplectic form. But that's not going to play immediate role to us. So this is somehow the geometry, basic geometry, behind the FBI transform. So any questions about this? So somehow philosophy is, and we will hopefully somehow elucidate it and see it, that this is now the phase space in the complex that corresponds to somehow it's the image of the real phase space, but now on the complex side. And one more comment, you see, what's the somehow philosophical importance of this being plurisubharmonic? Well, this is a holomorphic function of Z, because, you know, this is a holomorphic function of Z. Everything is a nice pairing, distributional pairing. So this is holomorphic in Z. Logarithm of a holomorphic function is a plurisubharmonic function, or if you just remember one variable complex analysis, logarithm of a holomorphic function is a subharmonic function. So this means that somehow it's natural to have spaces where the bound on your holomorphic function is given in terms of exponential of a subharmonic, or in this case, plurisubharmonic function. So these are phase space. So I want to prove a theorem. There's an H missing in the formula. Indeed, thank you so much, of course. There's an H missing, sorry about that, yes. So the theorem I'd like to prove now is this, that TH from Rn to H phi, which is defined to be L2 phi, our L2 space, intersected with holomorphic functions on Cn, is unitary. Okay? So this map here, if you map it into this holomorphic space, holomorphic functions, you see it's actually unitary. So observe, we are mapping functions of n variables to functions of effectively 2n variables, functions on C. So there has to be some overdetermined thing in this. The overdetermined part comes from the holomorphy with respect to Z. And then we have actually unitarity here between these spaces.
That's for any phi.
No, for any, so it works for any phi, which is a holomorphic quadratic form with these two properties. So proof, I'm not giving the best proof, but you know, best is the enemy of the good. So last time I just told you, and you could have done it if you felt like it, is that this, we already know that TH star, TH is equal to the identity on L2 of Rn. That just comes last time. That is a consequence of the Plancherel formula. So this is Plancherel. You see, you can think of this FBI transform in this setting, say, of this thing here, is that you are first have this Gaussian term, and then you take in the Fourier transform, and then you can undo this. So what we need to prove, that TH star, TH star is, so we know that it takes me to this space because of this. So TH star is an orthogonal projection onto H phi. So in general, you know, there's again linear algebra, but now in infinite dimensions. If I have a situation like this, TH, if I know this, then TH star is a projection, orthogonal projection onto the image of TH. So if we show that it's actually an orthogonal projection on H phi, we will know that this is so, okay? So for that, we do it as follows. We compute this. And the computation is based on just, you know, completion of squares. And I'll show you the formula. The formula is that this is equal to 2 pi h minus n. Then there is some stuff, though I will write it for once, z bar. And I write in generality, but, sorry. sorry, then it's pi h to the minus n, and then there is a 2 to the n, and then it's e to the 2 over h psi of z minus z bar, sorry, zw bar, I'm sorry, I need to integrate now, integration minus 2h phi of z, phi of w, and then you integrate it against uw dmw. This is actually the formula that you obtain, if you like, by completion of squares. Okay? And what is psi, of course? Psi is something which comes up in this business. Psi is the unique holomorphic, actually doesn't matter quadratic or not, but quadratic function on Cn cross Cn such that psi of zz bar is equal to phi of z. Okay. So what this means is that you can always, I mean, I'm not going to snow you with some vocabulary, but the linear subspace where z is z comma z bar, that is a totally real submanifold of Cn cross Cn. So a restriction of a holomorphic function to that submanifold determines this holomorphic function uniquely, and that's how psi is determined. But of course, in our case, it's all in the linear algebra case, everything can be computed. So what is psi? Well, phi of z, it's 1/2 imaginary part. So if I write it in z minus z bar thing, I get this hopefully correctly, yes? Z minus z bar is equal to 2i imaginary part of z. I square it, I get 4 times imaginary part of z square. I divide it with a minus, and I get 1/2 imaginary part of z squared. No? So this means that psi of zw, I call it z prime here because w here appears with a bar, is minus 1 over 8 z minus w squared. Is z prime squared. Okay. And this is an expression you get, okay? There is a little, I'm cheating just tiny bit because we have to, of course, discuss the convergence and so on, but let's just be a little formal here. So I need to show that this is the same as the projection, orthogonal projection. So rather than there is a more natural way of doing it, but I'll do it in this case, in our special case, in a sort of quick and dirty way. I now assume I am in this situation. And if you are asked, suppose your life depended on it, and somebody asked you, what is the orthogonal projection onto that subspace of L2 of phi? What would you do? Say, I mean, that's a mathematical problem that I would say I'd rather die than get into it, and GR is my favorite for that sort of thing. But here it's very elementary. How do you do it in linear algebra? You find a projector by finding an orthonormal basis, and then summing up this with that. So what is an orthonormal basis for H phi? Orthonormal. Well, first let's say orthogonal dense set. Well, you see, we should rewrite this in a more clever way, because every plurisubharmonic function can be written as a real part of a harmonic function, and another plurisubharmonic function which has better growth properties in the quadratic term, if I can find it, 2.2. You see, I'm going to write it as real part of minus 1/4 z square plus 1/4 zz bar. I hope I got the, it says here like that. You see, because the natural, so what would you, if somebody said, I want a basis of a space of holomorphic functions, what basis would you choose? Hey guys, this is elementary, this is like undergraduates. I'm teaching 500, huh? Z to the n, that's right. The trouble is z to the n does not integrate if I just multiply by e to the minus imaginary part of z squared. So what we need to do, we need to take out a holomorphic part here so that it will integrate with respect to now z squared. So the natural basis is z alpha, multi-index notation, e to the minus 1 over 4h z squared. This actually is an orthogonal set here. One has to prove it, but that's an exercise in complex analysis. So we have that, and then I have to compute, of course, z alpha. So now this is the integral z alpha z beta e to the minus 2 phi over h dm of z. So I'm not going to bore you with this, but I actually laboriously computed it, hopefully correctly, and what I got was 2 pi h to the n. You can, you do some gamma function type of thing, alpha infinity. This is what you get. So now I know what my projector is. My projector, the projector, if I call this pi phi u of z, sorry? What? Sorry? Is it times delta? Yes, of course, delta alpha beta. Thank you. This is an integral of a sum of, let's call these guys here C alpha inverse, of C alpha, well, minus 2, minus C alpha squared, because that's my normal, actually, I make it real. So C alpha squared times Z alpha, Z to the alpha, W alpha beta, U of W, and of course I integrate with respect to the correct measure, minus 2 phi W over H, dm of W. But you see, you can sum this sum. This is, it's basically summing Z to the power alpha W bar to the alpha divided by alpha factorial. But that's just nothing else but the inner product without any bars of Z and W bar e to the z. No, you know what I'm talking about. If you have a so this is a general fact, Z W bar alpha alpha divided by alpha factorial is e to the Z W bar. And there's this H, also H to the alpha. And there's some constants, which I forget, there's some constant here. But when the all dust settles, the point is you get exactly this formula. That's not the best way to do this, but it's a quick way to do this. So in other words, we showed now that this is indeed an orthogonal projection onto the image. By identifying it simply, you compute it using the linear algebra method, and you compute it by, evaluating what this does, and you get this. You could, but that's, it's still, to be honest, well, you could, of course, but it would be, it would be ultimately some computation like this. But you still would have to, just showing that it's the identity on holomorphic functions is not enough, because you still have to show that you get a full image. Well, maybe, but okay, that would actually give you the full image if you show it on this. But in any case, it's the way I decided to do it. So you see, so now we would like to talk about how differential operators act on the FBI transform side. So ultimately, what we would like to know is if I have a differential operator on Rn, which is what ultimately we are interested in, and I would like to see what sort of operator it corresponds to on the FBI transform side. So that operator has to act on a space like this. Okay? So any questions? Let me try. Well, you think of questions. I will try to do the German thing. And so, by the way, this projector pi is called the Bergman projector. And this is sort of the linear version of the Bergman projector. We need a little more experience here. So, what I would like to talk, and just rather than talk about differential operators, let's go all the way. And you know, I wish you never saw pseudo-differential operators, and you first see them on the FBI transform side. Pseudo-differential operators on the FBI transform. Now, if you have a pseudo-differential operator, what is pseudo-differential operator? You have a function on phase space from which you get an operator. Our phase space in this case is this lambda phi. So we should look at functions of lambda phi. Of course, functions on lambda phi are really functions on Cn because lambda phi is a graph. But it's good to think about it as functions on lambda phi. So we start with a function on lambda phi. And I will assume that the derivatives of A are all bounded by some, you know, minus n for some m, fixed m, let's say, fixed m. Okay, so I look at functions which decay, or you could even start with Schwartz functions for starters on lambda phi, and then we define the following operator: A, W, Z, H, dz, U is defined by the same formula as, you know, if you've seen differential operators, you will recognize the formula, except for some A, Z plus W over 2, zeta. Of course, this zeta has to be this, E to the I over H, zeta Z minus W, U of W. Something is wrong with your chalk. This is Jesus. And then I have to remember the order, d zeta wedge dw. So you should think, so this is a contour integral. And what's the contour? The contour is gamma sub phi. And this contour, gamma sub phi, well, it's the only contour that makes sense here, because zeta has to be inside of here, because that's what A lives. You see, a gamma phi is simply the contour where W goes to zeta equals to 2 over I dz phi of z. So you see, what it means now is that when you want to, you have to write d zeta and d zeta bar, And then you will get here dw bar dw, so you will integrate with respect to just the Lebesgue measure on Cn with some prefactors and the correct phase. Of course, we first have to, since everything now is in a complex, it is essential to know that this integral makes sense. And this integral will make sense, and I would like this integral to make sense as a map from lambda L2 of phi to L2 of phi. So I need to look at the real part of the phase because that will tell me how things grow or decay. But again, this is, in this setting, it is the linear algebra problem. I, z plus w over 2, that is equal to real part of I. So I cancels because I have 2 over I, dz phi z plus w over 2. Sorry, what have I done here? Z minus w. Z minus w. And now you can either take our phi from the example, which is, phi is 1 minus 1 over 8 z minus z bar squared, or do the general case using linear algebra. But when you do this, what you see is that this is equal to phi of z minus phi of w by linear algebra. This is a derivative of a quadratic form, so it's a linear function. I then take the inner product, no bars in this linear product, I take it with a linear function, so I get a quadratic function. So at least we got the orders of the polynomials correctly. Yes, it's quadratic in Z W, and it happens to be this function. So this is right, because you see, you're applying it to functions which sort of grow like phi w over h. This cancels it. And you're allowing grows like phi z, which this gives you. So this makes sense as an operator. And the kernel decays, because I made the assumption like this. So this is perfectly well defined. As an operator without any norm estimates, from AW Z H dz takes L2 phi minus L2 L2 phi. But we have more. A theorem. For actually A, which are merely for A such that merely d alpha A are bounded for all derivatives. A smooth function on lambda phi, AW Z H dz takes H phi to H phi, and the norm is independent of H. The norm is bounded, you know what I mean. Not the norm is dependent on H. How do you say it? The norm, let's just write it. Okay. Now, so I should just remind you of the sort of the classical and simple tool here for establishing L2 boundedness is the Schur's criterion. Schur's criterion says that if I have some operator K, so I use Alex's convention that the kernels are the same as the K, Z, W, U, W, the Lebesgue measure, then the norm of K is bounded by C if the K, Z, W, dm, Z and K, Z, W, dm, W are both bounded by C. So So it's a simple application of Cauchy-Schwarz inequality. And for instance, this way we saw the boundedness here, because once you take away those weights using this, well, this was decaying. So, but now we want to do it for functions which are not necessarily decaying, and also show that the norm is independent of h. This would not give you independence of h, because we would actually get the norm h to the minus n if we just use this. So we do it as follows. We do a kernel. I can't quite do the same letter here, obviously. So I write AW z h dz u is equal to an integral of k z w u w dm of w, where this k, now I plug in all the you know, what I have in the phase and so on. This is A, so I have this 2 pi h, and I have some minus a constant, then I have A z plus w over 2. Now I will skip the zeta. Zeta has to be, you know, it's just a function on the base, I could think of it. And then I have E to the 2 over h, z minus w, phi of z, z plus w over 2. Okay? Right? That's my kernel. That's what I have here. Constant here comes from d zeta, but that's just a constant because that's, you know, zeta is equal to this. So I have to take d zeta bar, d zeta and d zeta bar, but the only dw bar will contribute, and that will be just some constant determinant. And we know that this function, you know, is plurisubharmonic, so the determinants are non-zero. So I have this formula here. So first observation. So we first, you know, do it for things which are decaying, so that this all makes sense. This decays. We know that this phase exactly compensates for our L2 weights. It's dangerous business, this German erasers. So first observation, d zeta bar k is equal to dw bar k. Okay? The reason is that this dependence here is holomorphic. So d bar here dies. And here it's all symmetric, where it's just infinity. So we have this. And then integration by parts. Integration by parts shows that dz bar aw u is the same as minus aw dwu. And if u is holomorphic, this is 0 because we assume that this is in h phi, a holomorphic function. So this is the first thing. The second thing is the, oldest trick in this business, namely integration by parts, which eventually we applied as a sort of a definition, but first for decaying things. And what is that? Well, we notice that h dw e to the I over h z minus w zeta, so zeta is a function of w, and w bar is the same as I, actually, when all the dust settles, and let me just allow the dust to settle, zw, z minus w. This is a matrix, because, phi is a quadratic form, I differentiate twice, I get a constant matrix applied to this. It's just a calculation based on the definition of zeta w, which is, sorry, I made a mistake here, guys, and nobody caught me. This, of course, has to be zeta w over 2, because this is where we are, So if you differentiate with respect to w, you have z, w bar, so you get z bar here. when the dust settles, you get this formula. But this then allows you to build an operator with which you can integrate by parts, like, in the the oldest trick in this business, except now it's in the complex domain. And L is given by 1 plus phi zz bar inverse z minus w bar dw bar divided by 1 plus z minus w square over h. Okay? So we can integrate by part using this L, huh? And all the derivatives of A are bounded. But eventually we are going to get a lot of powers of this guy here, yes? So what this means that eventually this implies that this AW applied to U of Z is equal to, or if you like, is equal to this kernel KZW, but I put a tilde now, UW, DMW, and observe that we are on holomorphic function. So when I integrate by parts using dW bar, it does not do anything to U, huh? So what you get is where K tilde ZW is just equal to L transpose to the power n applied to A of Z plus W over 2, and that is O of 1 plus Z minus W squared over H to any power. And of course, I also have my prefactor, which is 2 pi H to the power minus n. Okay? To any power, negative power I want, well, minus n. Minus n, maybe I should take it 2n here, and then I get minus n there with the square. So now two things happen. We now reduced it to a kernel which has this nice decay property. And number two, if A satisfies this condition only, I can just use this as the definition of my, because this is equal to on functions which decay, but then extends to functions which do not decay. And what's the constant if we apply Schur's criterion? Well, that's the integral of this guy here with respect to either z or w. But that is in dimension 2n, because we're on Cn, real dimension 2n. So I'm gaining, I have a square here. So I'm gaining h to the dimension divided by 2. So I get h to the power 2n divided by 2, which is h to the n, and that cancels this term. And I have a constant which is independent of it. So now, one can do it. I don't want to do it just because it's technical. I gave a reference. One can change this to weaker, to things which are allowed to grow with some older functions, and make this into sort of Sobolev-like spaces, okay? Put basically, instead of just integrating respect to e to the minus phi, integrate it against some weight, like absolute value of z to plus 1 to some power. And all of this will carry on accordingly. So the last thing in the 10 minutes, I want to now deliver, the punchline, which is how do those things act on the how do we pass from real to to complex to the FBI transform side? So any questions when I'm fighting with this board here? Well, maybe I'll delete this proof. Now suppose I have a function, an operator which acts on the space on Rn. So I have A, which is a smooth function, or Rn, no, B, rather, so B on Rn cross Rn, such that the derivatives of B are all bounded, let's say. Or we can first assume again that they decay, though in this case it's already trickier. And then we define a pseudo-differential operator here as 2 pi h to the n, an integral of bx plus y over 2 psi e to the I over h psi x minus y u of y dy dxi. Okay? And this integral now is, of course, over R to n. Here, this integral was in a contour, which essentially was the only contour we can take for this to make sense. And now the theorem is this. And of course, you know, this is a non-trivial theorem. So this is Calderon-Vaillancourt theorem. Calderon-Vaillancourt shows that this BW XHD actually maps L2 to L2 in a way that's with a bound independent of H. This is just a recall what happens on the real side. So what we will, in our applications, of course, we are interested in differential operators. Last time I said alpha less than or equal to m dx alpha. So we'll be taking B essentially with some, I will want bxhd to be h to the power m p p. So of course you can say, well, this is not, does not satisfy this condition. That is correct. But as I said, there are some modification in the sort of Sobolev, replace L2 by Sobolev space, blah, 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 and you can deal with operators of higher order. Because this becomes now an operator which will have h to the power m here. And the principal symbol of this, from the semi-classical point of view, namely something which does not depend on h, will be the polynomial, the terms of order m, because everything else will have an extra h in front. So the theorem here says this, theorem, if B is like that, then TH B of XHD is equal to A Z H dz TH where A composed with K phi is equal to B. You see, K phi is this complex canonical transformation. Its image, the image of Rn cross Rn under this transformation is exactly lambda phi. So from a nice function on cotangent bundle of Rn, we get a function on lambda phi. And we know how to quantize the function of lambda phi. That's what we just did. You know, actually, this provides the simplest proof that I know, at least, of the Calderon-Vaillancourt theorem. Because you see, I erased it, but the proof of that this is bounded on L2, on H phi, is very simple. You remember, it was just this integration by parts and Schur's lemma. So if I have this formula, and we know this is unitary between H phi and L2 of Rn. So this means if this is bounded on H phi, then this is bounded on L2. So in fact, if we have this formula, I just gave a simple proof of this theorem, which normally goes through the Kotler-Stein lemma and so on. So how do we prove it? Well, the proof, not surprisingly, is based on, you can guess, completion of squares. All of this is very elementary in the linear case. I don't want to end up in allgemeine Krankenhaus, you know. Yes, sorry about that. I just don't know. No, I think I'm. Oh, I see. Okay, thank you. No, that's. I'll do it. I feel guilty about. I rather like it. I'm teaching calculus to 500 students, but in next semester. But they gave me a room with no blackboard.
Yeah, that happened to me. This is awful.
Yes, and I decided to do it like in medieval times. I'll just say something, and the students repeat. And then I say, we're going back to medieval times because I got a room with no blackboard. I wonder what would happen. I say, orientation of a bunch, repeat. This sounds very tempting. In any case, so the proof based on completion of squares, the proof is based on the following fact, which is this, that you see, if I want to think of this operator, then one way to think about it is this, that this is a superposition of linear functionals, which are obtained as follows: h of x star plus I over h dx xi star applied to u, b of x star xi star, and there's some integrated with respect to d xi star. Huh? I wrote it maybe a more correct version here somewhere. No, this is right. Yeah. This is right. Sorry, this is not quite b, but there is something which you obtain from b by the Fourier transform, whatever. It's just a way of writing a operator as a superposition of exponentials. So then all you need to show then that a z h dz w is equal to which is sorry. So what I need to show now rather sorry that th b h dx. Sorry. I have a moment, but all I want to say is that you see, you want to show, you want to write an operator now, this x h, sorry, z. Oh gosh, Sorry, I'm over time, but I just want to say it. And as I said, I gave a reference where it's very clearly done. But my point simply is that a w z h dz w should be now e to the I over h, and I write it as k x star xi star z plus w over 2 plus I over h z minus w theta, and then I'll have this bx star psi star dx star psi star, and then of course I apply this to, and then I have to integrate against uw d zeta dw, and of course I have my 1 over 2 pi I and all that. And what you need to show that this linear form here on lambda phi is the pullback of this by the inverse of k phi. So all you need to check is this formula, not for arbitrary A, arbitrary B, but for B simply being an exponential of a linear function. And once you do this, you write it out, and it's a completion of square exercise. Huh? Yes. And then, of course, there's some justification needed, but it's not so hard. You just write this formula. So I gave in my, as I remind you, if you go to my homepage, I did not provide notes, but I provided detailed references to for instance, where this is proved very clearly by Michael Hetrick, for instance, or in my book. And here I will end, but you see we are getting close to our goal. I want to remind you that our goal is to show that the wavefront set of U is contained in the wavefront set A of PU union the characteristic set of P, characteristic set being the set where P is where the principal symbol of P vanishes. And the point is that, you see, if we just have B, which is C infinity, we are trapped in lambda phi. We can't move off lambda phi in our quantization. However, if this B is analytic, which is the assumption here, this coefficient is analytic, I can deform it into the complex. So what this means is I can move off lambda phi, and by moving off of lambda phi, that effectively changes lambda phi to some lambda phi with a different weight. And this different weight will be our delta gain, you see. So I'll prove it under a simplifying assumption of sort of global holomorphy near the real axis. But then I think the argument will be very clear. So my next thing will be to show how, under the assumptions of analyticity, we can move off of lambda phi and still get boundedness between the spaces with a new weight. And those spaces will be the same spaces as functions, but the norms will be different. And this difference in norm will be our gain of delta. And to do this, we will have to understand how on the FBI transform we can approximate the operators given like this by multiplication operators using an idea that goes back to Cordoba and Pfeffer. Yeah. Okay, so sorry to go over time. Thank you for your attention. Complex conjugate. Oh, you mean like in a Legendre transform? Yes. So there is a yes, but I can't remember now. But there is a way of thinking about the weights in terms of Legendre transform. But I did it. Maybe Jean-Kai remember. No, just kidding. I did it in my course 2 years ago, but I forgot now. Yeah. But you are right, there is a way of thinking about transforming weights. But in this case, it may be a little different. That was more like that you start with a weighted space, and then you apply sort of a local Fourier transform. And in that case, indeed, the weight, so maybe that's not quite right here. But if you, for instance, take a weighted space, and then you apply to it a Fourier transform in some microlocal way, then what you get is something in a new weighted space, a holomorphic function new weighted space, and the weight is some kind of Legendre transform of your original weight. But I would have to remember that. But this one I'm not sure. Mm-hmm.